Alright, so what I want to do today is I want to talk about the change of variable formula just in polar coordinates. And I want to use this as an opportunity to talk about some stuff that you should hopefully have seen in Calc 1, but almost surely have not seen in Calc 1. So I want to go back and I want to ask an old question. What is the limit as x goes to 0 of x squared plus, well, let's do x squared over sine of x. Anybody remember how you would do that?
L'Hopital's rule?
L'Hopital's. I saw some pauses, so let me give you an easier one. What if I gave you e to the x minus 1 and x? How would you do this?
Yeah.
I'm sorry?
Is it also L'Hopital's?
Also L'Hopital. Okay. You guys seem to really like L'Hopital. Let's do one more. Sine of x over x.
Also L'Hopital's rule? Oh,
Also
no.
L'Hopital's rule?
Yeah.
Alright, so how would you use L'Hopital's rule? L'Hopital says this would be the limit as x goes to 0. What's the derivative of the top? Cosine. What's the derivative of the bottom? Right, and as x goes to 0, cosine of x goes to 1. Right, everybody comfortable with this? Congratulations, you've all failed Calc 1. What's the derivative of sine? Cosine. How do you know the derivative of sine is cosine? Sine prime of x is the limit as h goes to 0 of the sine of x plus h minus the sine of x over h. Let's take the derivative of sine at 0. You get the limit as h goes to 0, sine of h over h. What limit do you need to know to calculate the derivative of sine as cosine? You need to know the limit as h goes to 0 of sine of h over h is 1. So if you're using L'Hopital's rule to solve this, you're doing a circular argument. In a very real sense, since trig functions are circular. Okay? I thought this would be a good way to start today's class because it is so easy to not realize when things have been proven carefully. And so in a lot of the stuff we're going to be doing today, we'll need things such as the area of a circle, or maybe the perimeter of a circle. If you know these or if you don't know these, it makes things very difficult or very easy. So over here, if I know the derivative of sine is cosine, this is not a difficult limit to calculate. Unfortunately, if I don't know that, I then have to do this in a very difficult, complicated way. And we somehow need to prove what is the limit as x goes to 0 of sine of x over x. So if there's time later today, I will go through at the end of how you would actually calculate that this limit is 1. It turns out this is the only limit you really need to understand to calculate all the derivatives of trig functions. Everything follows from this limit. Okay. Any questions on this calculation? Okay, has everybody written this down? Alright, so what I want to do now is I want to calculate the area of the circle. If a circle has radius r, the area is pi r squared. Okay? I'm only going to calculate the areas of circles of radius 1. And the reason is area is going to scale like radius squared. So if I can do it for radius 1, I can do it for any radius. So area of a circle. So we need this if we're going to do the polar change of variable formula. Alright. So we'll take a circle of radius 1. How many of you have seen the n-gon approximation to the area of a circle? So what I can do, I'll do it with 6 sides. So I'll use a hexagon. And what I can do is I can write my circle almost as a hexagon. I'm going to miss a little bit. I'll miss a little bit of the caps. And so this is the inscribed hexagon. Instead of doing an inscribed hexagon, what could I do? Circumscribed. It's been a while since you may have seen these words. Inscribed, n-gon. Here, n equals 6. So what I can do is I can calculate an approximation for the area of the circle by just calculating the area of the hexagon. This will be a lower bound. If I do a circumscribed, I would do an upper bound, and then I take the limit as the number of sides goes to infinity. So this goes all the way back to Archimedes, and this gave us great approximations, and in the limit, you will get pi. So let's try to calculate what is the area. So I have n sides. And so let's see what one of the triangles is going to look like. What's the length of these two hypotenuse? Hypoteni? 1. Because it's a circle of radius 1. If I had a circle of radius r, it wouldn't be too difficult to change. What's the measure of this angle over here? Just this upper part.
360 divided by 6.
360 divided by
6.
Okay, if it was a hexagon, if I divide by 6, it would be the whole angle here. I only want just the top part. So it would be 360 divided by 12, or in general, 360 divided by 2n. How many of you know why we use radians and not degrees? No one's ever wondered why they've been forced to do things in radians and not degrees? I will do things in radians for now. I know why it's better to do things in radians, so I'm going to just leave this for now. You could, of course, write this as 360 over 2n if you want. Now we can calculate what is the area of the triangle. So if this is 1, what's the length of that side? Okay. And so it becomes... So I have a triangle, I have the angle, I want the opposite side. So it's just going to be the sine of 2 pi over 2n. This over here would be the cosine of 2 pi over 2n. So the area of the big triangle is going to be 1/2 the base cosine 2 pi over 2n times the full height, which is going to be 2 sine 2 pi over 2n. Okay? And how many triangles do we have? N. So the area of the n-gon is going to be, the 2 cancels with the 1/2, so we'll have n cosine 2 pi over 2n sine 2 pi over 2n. And this is going to be a lower bound for the area of the circle. And as n gets very large, this is going to be an extremely good estimate for the area of the circle. Okay? As n gets very, very large, what does the cosine of 2 pi over 2n go to? It's going to go to, the argument is going to go to 0. I'm going to be evaluating cosine at 0. It's going to go to 1. What's the sine of 2 pi over 2n going to go to? Damn. I've got a 0 here, and I've got an infinity over here. So I've got an infinity times 0. So we're going to have to be careful. Okay? I can write this as the following way. It's going to equal cosine of 2 pi over 2n. And I love multiplying by 1. So I'm going to multiply by 1 in the following way. I have the sine of 2 pi over 2n. And n in the numerator is the same as a 1 over n in the denominator. If you're not sure, if you multiply by n over n, the n's cancel down here. Well, I have a sine of 2 pi over 2n, I have a 1 over n. Let's make this a 2 pi over 2n. Well, I can't just multiply the denominator by 2 pi over 2, I have to multiply the numerator by 2 pi over 2. Well, what's 2 pi over 2? Pi. So now we get the following. We'll move the camera. Can you move the camera just a bit? So now the area of the n-gon is cosine 2 pi over 2n sine 2 pi over 2n over 2 pi over 2n times pi. We now take the limit as n goes to infinity. And what do we get? So what do we get as n goes to infinity? This part was no problem. Cosine of 2 pi over 2n, that goes to cosine of 0. That's just going to be 1. This looks like the sine of h over h, right? It's like h equals 2 pi over 2n. What is the limit as h goes to 0, the sine of h over h? We started class with that today. 1. Now you see why this limit is so important. That limit is going to give us the area of the circle. Because that limit is 1, as the limit as h goes to 0 of sine of h over h equals 1, the area is going to converge to pi. And so here is a proof that the area of a circle is pi. Technically, I just proved that it's lower bounded by pi. You can do an analogous argument for an upper bound with circumscribing. Assuming we know this one limit. Okay. We may not have time to get to that limit today. We may have to do that limit next week. But everything in trigonometry, everything comes down to this one limit. Okay? Any questions on how we calculate the area of a circle? So we now know the area of a circle is pi, or if it's radius 1, or in general, pi r squared. A very similar calculation would give us the perimeter is 2 pi r. How would I calculate the perimeter? What would I use? Yes? The perimeter from the...
For the n-gon.
Excellent. So for the perimeter, you would use the n-gon perimeter. Perimeter from the n-gon perimeter. So we can calculate the perimeter of the n-gon very easily. It's just this sign stuff over here. And you'll see it's going to be the same limit. You'll see a pi coming in again. The difference is we won't have a factor of 1/2 anymore. And we won't have a factor of cosine. Not a big deal. And that's why you'll get 2 pi rather than pi. All right, so now we know the perimeter, now we know the area. This is actually the reason why we work in radians. The reason we work in radians is the perimeter of a circle of radius 1 is 2 pi. That's also the angular measurement. So this is an extremely important point and is essential in the change of variable formula. Okay, so if you can swing the camera back. So, how much of the circle do I have here? How much is this angle, percentage-wise? 1/4, 25%. The perimeter is, oh, it's a half or two, is 2 pi. Give me 2 different ways to refer to this angle. Yes?
Pi over 2.
Pi over 2 and 90 degrees. Right. Those are the 2 ways. Here's why pi over 2 is better. Here's pi over 2. What is the length of that part of the circular arc? Pi over 2. This is why we use radians. When you use radians, the angular measurement of a unit circle is the length of the arc. If you had a circle of radius r, it would be r times pi over 2. Again, if you use things in degrees, it's not a big deal, but you have to put in a conversion factor. This is the nice thing about radians. Okay? Any questions about this? So the radians gives you how much this is in terms of the length of the arc, and it gives you the angular measurement. It turns out if you try to calculate the derivative of sine, it's kind of nice that the derivative of sine is cosine, and the derivative of cosine is minus sine. If you measure sines and cosines in degrees, it is no longer true that the derivative of sine is cosine. It differs by a factor of 2 pi over 360. Okay? And it's because of how the limit is done. The limits change because you've rescaled things. When you're looking at the limit of the sine of h over h, if I have this angle here, I'm changing the number if I'm measuring it in degrees or radians, but I'm not changing the physical value of sine. The physical value of sine is referring to something in space. You give me a physical angle like this, h, that's sine. But the denominator does change. So if I change from degrees to radians, this ratio is going to change, the limit is going to change, the derivative of sine is going to change. So the derivative of sine is only cosine if you work in radians. So this is one of the points that is often glossed over in trig and Calc 1. We've got to be careful. Okay, why do I care so much about this? What's our goal? Our goal is the polar change of variables for integration. And we have a dx dy in Cartesian coordinates. What do you think we should have in polar coordinates? Yes?
dr d theta.
dr d theta. I'm going to deliberately write it like this because dr d theta can't be entirely correct. So if you think about things, dx and dy, if they're both in meters, this is in meters squared. So this is meters, meters, meters squared. This is in meters. D theta is unitless. It's an angular amount. It doesn't have length in meters. This is going to be the wrong units. What can I do to convert d theta to being a length?
Multiply by r.
If I multiply by r, if I now talk about the length of this arc here, if I do r d theta meters, I get meters squared again. Okay? In no book will you see people writing dr r d theta. This is a notational nightmare. Am I talking about maybe the derivative of r squared? It's extremely confusing to write it like this. How should you write it? Yes?
The r in front.
Yeah, we should move the r in front. And we normally write it as r, this is hard as a Bostonian, r dr d theta. Okay? I like to write it at least once as dr times r d theta to remind you where the r is coming from. Think of it as the conversion rate. I'm converting from Cartesian coordinates to polar coordinates. This is the cost. Okay? I need to measure the theta in the right units. Okay? Any questions so far on the motivation and what we're going for? Alright, so now I'm going to state the polar coordinates change of variable. So this should go without saying, but what region do you think we want to integrate over for polar coordinates?
Circle.
I'm sorry?
Circle.
Circles. You can use it for non-circular regions. How many of you did things like lemmasates and cardioids, all those years ago? These shapes are much easier to write down in polar coordinates. You can do stuff like that. Polar coordinates are nice for that. But if you had your pick, you'd like a circular region. So the idea is the following. So change of variables. Have some map T goes from R to S. You have variables x1, xn go to u1, un. And the idea is you're integrating over S of f of u1 un du1 dun should equal integrating over t some function f of u1 of x1 through xn dot 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 un x1 through xn times the conversion factor of x1 through xn dx1 through dxn. So this is the general framework of a change of variables. I have some region S where I have my u variables. I have some region T where I have my, some region R where I have my x variables. I have some way to map from the x's to the u's. So this would now give me a nice function. These are going to be evaluated at the right point. And I'm going to have some kind of conversion factor. The conversion factor is going to be like the r d theta. And so what I want to do is I'll write down the formula for polar, and then I'll talk to you about why it's true. So the integral over a disk of radius r of f of xy dx dy is equal to the integral of f of r cosine theta r sine theta r dr d theta. I'll do a disk of radius big R. So little r goes from 0 to big R, theta goes from 0 to 2 pi. So this is the change of variables in polar. This is the special case. I'm not sure how much we're going to do in the general case. We will definitely do the change of variables for spherical and cylindrical. Okay, these are the big three. Okay, so the goal is to try to understand where this formula comes from. We at least have some idea of the reasonableness of this. So again, before you do a long calculation, it's nice to get a sense of, do we expect it to be true? I can't have just dr d theta. That's not going to transform properly. I need to have an area. R dr d theta is the simplest thing I could do. My function f is defined as a function of x and y, but I want to now look at a new function of r and theta. If you want, you could consider this function g of r theta. It's my new function that depends on r and theta. And I get it by taking my original function, and wherever I have an x, I put in an r cosine theta. And wherever I have a y, I put in an r sine theta. Which would you like to see first? An example using the change of variable formula, or a proof of the change of variable formula?
Example.
Example? All right, let's do an example. What is the simplest function I can look at that I will allow you to use? I will not let you use the zero function. 1. All right, let's look at the function 1. We want to integrate over the unit disk the function 1 dx dy. Okay? So I have to figure out what the bounds of integration are. Is this region vertically simple, horizontally simple, or both? Both. All right, do you want to integrate up, or do you want to integrate left, right? Up, or left, right? Up, right? We're all used to integrating up. If we integrate up, we need our, here's our y1 of x, here's our y2 of x. And the equation of the circle is x squared plus y squared equals 1. So y is plus or minus the square root of 1 minus x squared. One of these is going to be the bottom, one of these is going to be the top. Which one do you think is the bottom?
Negative.
Negative. So y1 of x is negative square root of 1 minus x squared. y2 of x is the square root of 1 minus x squared. Alright, so I can write down my integration. X goes from minus 1 to 1. Integral y goes from minus square root of 1 minus x squared to the square root of 1 minus x squared of 1 dy dx. Sorry?
No.
Okay. If I wanted to, I could actually exploit some symmetry. if I can figure out the integral just in the top quarter, I could do it and just multiply by 4. So I want you to get used to looking at things symmetrically. So this is the same as 4 times the integral x goes from 0 to 1, integral y goes from 0 to the square root of 1 minus x squared, 1 dy dx. Okay? If you don't see this, you can of course just keep it like this, but if you can start to notice this, you can make your life a lot easier. What's the integral of the function 1? Y. So we get root 1 minus x squared minus 0, we just get square root of 1 minus x squared. If I hadn't done that, I would have had twice that. Alright, so I have 4 integral x goes from 0 to 1 of the square root of 1 minus x squared dx. Anybody remember the antiderivative of square root of 1 minus x squared? Guys, your memory is terrible. It's 1 half x square root 1 minus x squared plus 1 half arc sine of x. And of course we have to put in the factor 4. Then we evaluate this at 0 and 1. Okay. When I evaluate this at 1, what do I get? 0. When I evaluate this at 0, what do I get? Good. 4 times 1 half is 2. What's the arc sine of 1? What angle has a sine of 1? Pi over 2. And what angle has a sine of 0? 0. Yay! The area of the unit disk is pi. How many of you did not remember this? I had to check it this morning. What can you do? I'm sorry?
Look it up.
You could look it up, but what could you do? All books have been burned, it's sad. You can take the derivative of this. Now, it's not necessarily fun to take the derivative of arc sine, but you can take the derivative and check and make sure it works. That's the nice thing about antiderivatives. You can check and see if you're right. So again, how you would find this is difficult, but now that we have that as a guess, we can check and see if it works. What this should hopefully convince you of is that this is not a fun problem to do in Cartesian coordinates. Okay? You need to know how to do integrals of the square root of 1 minus x squared. How many of you know an integration technique that might be useful here? What might be useful for a square root of 1 minus x squared? Trig substitution. The dangerous thing in trig substitution is, did you ever need to use the fact that, oh, I don't know, you have a certain limit equals 1, that the area of a circle is pi? What did you need to use to prove trig substitution? So this is a way to bypass trig substitution and make you appreciate trig substitution. Alright, so let's do it again, but now let's do it in polar. So now, the integral over the unit disk of 1 dx dy, I'm sorry. So now, can you turn the camera? So now if I want to integrate this over the unit disk, what do I say? It's the integral of my function f at cosine theta, sine theta, dr d theta. R goes from 0 to 1, theta goes from 0 to 2 pi. What's the function f here? My function f of xy is what? What's my function f of xy?
Circle.
I'm sorry?
It's a circle.
Well, I'm asking, what function am I integrating? 1. My function's identically 1. So what is my function if instead of x and y I put in r cosine theta and r sine theta? What do I get? 1. Right? It's still a very nice function. Alright, so I integrate, theta goes from 0 to 2 pi, r goes from 0 to 1 of 1 r dr d theta. I actually have a rectangular region. I could do the integration in either order. I could switch orders very nicely. What does a circle look like in polar coordinates? Box, rectangle. So here's theta, here's r, here's 1, here's 2 pi. My circle is a box. Okay? This is the advantage of changing regions. Okay? Okay, so now I integrate with respect to r first. What do I get when I integrate r? R squared over 2, evaluated 0 and 1. Alright. Well, r squared over 2 at 0 and 1, that's just 1/2. So I'm now just integrating 1/2 d theta. Alright, well that's not so bad. That's just 1/2 theta, evaluated 0 and 2 pi. So 2 pi divided by 2, it's just pi. For those of you watching this at home, you can't see both examples right now, but if you remember from what we had a moment ago, you can see that this is a much easier calculation. Okay, so the time we spend proving the change of variable formula is going to be time well spent. Okay, it allows us to convert integrating over horrible regions, and yes, back to the Hamantash and Lockyer debate where a circle is horrible. It allows us to convert horrible regions like the circle to nice regions like rectangles. And again, for the purposes of integration, rectangles are our favorite shape. Okay, any questions about this example?
I don't get why it's a 1. Like why the function is 1.
Because that's the function I'm giving you. I'm saying I want to integrate the function 1 dx dy.
Yeah, but like why do we want to, like why does that give us what we're looking for?
Well, that's going to give me the area of the disk because I'm integrating the function 1 over the whole region. So that just gives us the area. Think of it as it's a density of 1, so it's going to give me the total mass. Or if you want, think of it as I go 1 unit high. So if I go 1 unit high, I'm going to have basically a cylinder, and the volume of the cylinder is going to be the height times the area of the base. And so the area of the base now is exactly what I'm getting here. So this just gives me a way to calculate the area of the region. Okay. Any questions about this calculation? Yes?
When you integrate it in terms of r,
Yes?
why is it r squared over r over 2 when it just be r?
Because I have r dr. So the r that comes from the change of variables is the key fact.
Okay, so it's like part of the function that you're integrating.
So the function I'm integrating is f. The function I'm integrating with is 1, but when I convert to polar coordinates, the function actually changes by this factor of r.
Okay.
So the fun name for this is the Jacobian of the change of variable formula. You can also look at it as how the area element transforms. The dx dy becomes an r dr d theta. But now that you have it here, this r comes over and is now part of the function we're integrating. So the only thing we're left with is we have to prove why this formula is true. Okay. Any questions on this calculation? Alright, so now let me give you an idea of why this is true. So fortunately, at the start of class today, we proved that the area of a circle is pi r squared. So why is the change of variable formula true? So if I have a regular region, this is what we've been taught to do in terms of Riemann sums. We chop it up into little pieces, x's and y's, and we have small delta x's and small delta y's, and we have these small rectangles. Let's look and see what happens with the circle. Yeah, this is about the best I can do. Yeah, this is not going to be, well, this is not even going to be remotely drawn to scale. So here is a circle of radius r, and I'm going to increase the circle by a small amount delta r. And, I have some angle here, theta, and I'm going to increase the angle by a small amount delta theta. And so I'm now going to get a small area patch over here. So I want to figure out what is the area of that little patch. Well, rather than calculating the area of this little patch, can somebody give me the area of this whole moat? So the area of moat. So what would be the area of the moat between the two circles? Yes?
It's going to be 2 pi r plus delta r minus 2 pi r.
So 2 pi r plus delta r is going to be the perimeter.
Oh, you mean pi r squared. Pi r
Okay.
plus delta r
So
squared.
pi r plus delta r squared minus pi r squared. That's going to be the area of the moat. And so when I expand, I'll have a pi r squared that cancels this, and I'll get a pi times 2r delta r plus delta r squared. So that's going to be the area of the entire moat. What fraction of the moat do I have? So what fraction of the moat? Yes?
Theta divided by 2 pi.
Almost. You're off by one
Delta
symbol.
theta.
Delta theta. Right? Theta over 2 pi would be the area of this big block over here. I want the area of the infinitesimal patch. So a small patch is delta theta over 2 pi. That's the fraction we have. If delta theta happened to be 2 pi, it would be a disgrace to call it delta theta, but then it would be the whole thing, and we would have a fraction of 1. If delta theta was, half of the circle, again, that's ridiculous, it would then be pi over 2 pi, that would be 50%. So we get delta theta over 2 pi times, I'll bring the pi in, we'll get 2 pi r delta r plus pi delta r squared. And so now, when I do the algebra, the 2 pi's cancel here, and I get r delta theta. And over here, one of the pi's cancel, and I'll get 1/2 delta r delta theta. So now when I'm doing my Riemann sums, this is essentially what I have. Now what happens as delta r and delta theta get really, really small? This is going to go and start looking like r dr d theta. What do you think this piece will look like? We're going to have a 1/2 dr d theta, but I'm going to have this extra delta r over here. And so as r gets really, really small, this is going to be 0. It is an extra order term. When I'm talking about areas, I shouldn't have 3 deltas. I should only have 2 deltas. Okay? So here, this makes sense that this is going to become a dr d theta. The delta r becomes a dr, the delta theta becomes a d theta. This has one extra piece. Okay? Any questions about this? So again, this is, you can ask yourself as to how much of a proof you consider this. If you consider this an incomplete proof, you have a good intuition. It's not a completely rigorous proof. I think for a first course in Calc 3, this is the right level of detail to get into. If you would like to see more details, let me know. But this is hopefully enough to give you a sense of why the change of variable formula works. Why does dx dy become r dr d theta? Where's that extra r coming from? I want you to get enough of a sense to see that. If you really want to see more, by all means talk to me. I'm happy to either give you something to read or to meet with you, or continue to advanced math classes. You probably have guessed by now that I am a math geek. I took a very tough class freshman year, and at the end of the year, it's a unified class on multivariable calculus, linear algebra, point set topology, and vector analysis, all in one class. I was, I think, the only one who liked the class by the end of the year. And we had extra time at the end of the semester, in the spring, so the professor decided to prove the change of variable formula in full generality. My memory may be a little faulty, but I am pretty sure we used every letter in the English alphabet and every letter in the Greek alphabet in doing this in such great generality. I believe I was the last student in the class to stop paying attention. And eventually it did reach the point where even I gave up. As much as I loved math, it was just too much. You do not have to have that much of an alphabet soup, but things start to become notationally complicated. You have all your different regions and your maps between them, you have your coordinates here, and you have your indices. It can become a nightmare. I want to try to do some special cases in this class, the most important special cases. So let's do another example. Let's integrate over the unit disk the function, the square root of 1 minus x squared minus y squared dx dy. Do you want to integrate with respect to x first or with respect to y first? Yeah. The shrugging shoulders is the correct answer. It doesn't really matter, right? Do you want to integrate with respect to x or y? No. You have to find what is the antiderivative of the square root of 1 minus x squared minus y squared. Now I showed you the antiderivative of the square root of 1 minus x squared. I will erase this immediately. 1 minus x squared minus y squared, this is just showing off, is the square root of 1 minus y squared minus x squared, is pull out a square root of 1 minus y squared, square root of 1 minus x over 1 minus x squared of 1 minus. You can start trying to play games like this and try to renormalize and try to, now y is fixed, so this is some kind of new constant, change variables by sending x to 1 over the square root of 1 minus y squared times x, and do a change of variables like this. Okay? Yes. To be erased. What should we do? Convert to polar. So my function f of xy is the square root of 1 minus x squared minus y squared. F of r cosine theta, r sine theta, what will that be? It'll just be the square root of 1 minus r squared cosine squared theta minus r squared sine squared theta. Ooh! What does that simplify to? 1.0.
1.
1 minus r squared. Cosine squared plus sine squared is 1. So this becomes 1 minus r squared, with a square root, of course. Alright, so now I get the integral of my function is the square root of 1 minus r squared. How many of you are happy about integrating a function like the square root of 1 minus r squared?
Isn't it 2r squared? Because you have 2.
No, cosine squared plus sine squared is 1.
Never.
Anybody happy about integrating a square root of 1 minus r squared? Isn't that the whole issue that got us on this, change of variable formula kick? Because we didn't want to integrate the square root of 1 minus x squared. Now we're going to be integrating the square root of 1 minus r squared. I'm sorry?
Can you change it again?
You already changed it to a disk. If I change it again, I go back to the circle.
Stop.
But is this the whole thing? Actually, I think you were the one who made the comment earlier. What else do I have after the square root of 1 minus r squared? R, dr, d theta. And weren't you the one who made the comment that the function we're integrating is multiplied by r? If you had your druthers, right, when you have the square root of, that's I think the right word, the square root of 1 minus r squared, what do you want to have following a square root of 1 minus r squared? I mean, again, ideally a negative 2r, but that's too much to hope for. And r is not so bad. So r goes from 0 to, let's do, the unit disk is 1. Alright, theta goes from 0 to 2 pi. It's a rectangle. I could integrate the theta first. And so what I want to do now is we've got a couple of minutes left. I want to just do this integral somewhat carefully and just be a little bit more free in terms of the order in which I do things. I'm integrating over a rectangle. This has no theta dependence at all, so I can write this as the integral theta goes from 0 to 2 pi of d theta times the integral r goes from 0 to 1 of the square root of 1 minus r squared r dr. And again, the reason I can separate things like this is I'm integrating over a rectangle. There's no theta dependence in the square root of 1 minus r squared. If you don't want to do it this way, do the r integral first and then do the theta integral. I'm just doing it like this because what does the theta integral give me?
2 pi.
2 pi. So I have 2 pi, and I want to integrate r goes from 0 to 1, 1 minus r squared to the 1 half, and I'm just going to be very pedantic, negative 2r dr, and so what do I have to multiply by? I can't just multiply by negative 2 as much as I'd like. Negative a half. Or if you want, you could do u substitution and do it slowly through u substitution. I'm just setting myself up, so now I get 2 pi times negative a half is negative pi, and I get 1 minus r squared to what power? 3 halves. And then I have to divide by 3 halves. And I evaluate it at 0 and 1. Okay? Okay. And now when I plug in 1, what do I get? 0. When I plug in 0, what do I get? I get... Okay. Good, everything's right. For a second this looked wrong, but no, this is right. I get 2/3 pi. Does anybody recognize 2/3 pi? We've just computed one of the most important numbers ever. Yes?
Is that E?
No. Not a bad guess.
Really excited first.
I know, no. You will still be really excited at the end. What I've done is I take a circle and I'm going up to a height of the square root of 1 minus x squared minus y squared. So if I let z equal the square root of 1 minus x squared minus y squared, this becomes z squared is 1 minus x squared minus y squared, or x squared plus y squared plus z squared equals 1. What have we just calculated?
Distance formula?
Not the distance
Sphere.
formula. The sphere. Not the whole sphere. We've calculated the volume of the top half of the sphere. Okay, if I can calculate the volume of the top half of the sphere, I can do the volume of the bottom half of the sphere. What's the volume of a sphere? 4/3 pi. And if instead of having a sphere of radius 1, I had a sphere of radius r, all you would get is an r cubed. So we have shown volume of a sphere of radius big R is 4/3 pi big R cubed. That's a pretty nice dividend for one lecture. Now, of course, I owe you a proof of the limit formula for sine. And so, based on the fact that we have 2 seconds left, I am not going to get to that today. So I will owe that to you at some point in the semester. This is the power of the change of variable formula. We got very easily this area of the unit disk. Well, that's not so impressive because we kind of built that into the formula. But we got the area, we got the volume of the sphere. And that's pretty nice. Okay.